First, we will discuss about the rotational energy levels of a rigid diatomic molecule, and then we will discuss how can we get the Raman spectrum from the rotational energy levels of the rigid diatomic molecule. So let us start. First, let us consider this schematic which shows the rigid diatomic molecule, and the atoms in the molecule are separated by the distance r0. The molecule rotates end over end about a axis passing through the center of mass. In such case, the rotational energy levels of the rigid diatomic molecule in quantum mechanics is given by Ej equals to j square by 2I. Here j refers to the total angular momentum of the rigid diatomic molecule. So the eigenenergy of this system will be Ej equals to h cut square times small j plus 1 divided by 2I. Here I is equals to mu r0 square. Mu is the reduced mass of this system, that is m1 m2 by m1 plus m2. So the moment of inertia I equals to m1 m2 divided by m1 plus m2 times r0 square, and the small j is our rotational quantum number for this rigid diatomic molecule. Now, in the case of Raman spectroscopy, we usually represent the Raman spectrum or Raman shift in terms of wave number. So we will convert this energy of this rigid diatomic molecule in terms of wave number. So in terms of wave number, the energy of the system small Ej equals to capital Ej by hc. Here h is the Planck's constant, c is the speed of light in the vacuum. So the energy of the rigid diatomic molecule in terms of wave number is equal to h cut square times j into j plus 1 divided by 2I hc with the unit centimeter inverse. Here j can take the values any positive integer including 0. So the energy levels of the rigid diatomic molecule or rigid rotor in quantum mechanics is given by small ej equals to h by 8 pi square ic times j into j plus 1 with the unit centimeter inverse, that is in the wave number. The rotational energy levels for the rigid diatomic molecule Ej equals to B times j into j plus 1 centimeter inverse. Here B equals to h by 8 pi square ic centimeter inverse. This constant B is known as rotational constant. The selection rule for the rotational quantum number is given by del j equals to either 0 or plus minus 2 only. So this condition gives the possible allowed transitions in the Raman spectroscopy. For transitions from j to j plus 2 step, that is del j equals to plus 2, we represent it as S-branch line. The excitation energy for S-branch line, that is del j equals to 2 line, equals to del ES, that is given by B into 4j plus 6 centimeter inverse. That can be obtained by putting here j plus 2 in this expression, and then we have to subtract the Ej for j equals to j. So the difference will give this del ES, that is the excitation energy for the S branch line. Now, if mu Ex bar is the wave number of the exciting radiation on this molecule, then the wave number of the corresponding S branch lines are mu S bar equals to mu Ex bar plus minus del Es centimeter inverse. So here mu S bar is the wave number for the corresponding S branch line, mu Ex bar is the wave number of the exciting radiation, and del Es corresponds to the wave number for the allowed transition in that S branch line. So we can write nu S bar equals to nu Ex bar plus minus B times 4j plus 6 in centimeter inverse. Here plus sign refers to the anti-Stokes line. This line comes due to the photon emission by the molecule, and the minus sign refers to the Stokes line. This line comes due to the photon absorbed by the molecule. So we'll discuss these anti-Stokes line and Stokes line in details in the upcoming slides. Let us discuss about the Stokes line and the anti-Stokes line in Raman spectroscopy with the help of schematic diagrams. So the left schematic diagrams refers to the Stokes transition in Raman spectroscopy. Let us consider two energy levels having the rotational quantum number J and J plus 2. So the rotational quantum number J will give the lower energy level and rotational quantum number J plus 2 will give the higher energy level. Now the incident radiation on that diatomic molecule system has the wave number nu Ex bar. So the molecules at the energy level having rotational quantum number J will be excited to a virtual energy level having the energy nu Ex bar. And then the molecules will release its energy and they will come back to the higher energy level having rotational quantum number J plus 2. So the emitted radiation have the wave number nu Ex bar minus B times 4j plus 6. So if we see carefully, the emitted photon or emitted radiation has the energy less than the energy of the incident photon. So some energy from the incident radiation is getting absorbed in this system. So for the Stokes line, the S branch line to the low wave number side of exciting line. Similarly, for the case of anti-Stokes line, we'll consider the molecules are getting excited by absorbing the incident photon from the higher energy level, that is the energy level having rotational quantum number J plus 2. So the molecules will be excited from this J plus 2 energy level to a virtual level having the energy nu Ex bar. Now after releasing the energy, the molecules will come back to the ground state, that is the lower energy level having rotational quantum number J. So the emitted radiation or the emitted photon has the energy nu Ex bar plus B times 4j plus 6. So it is clear the emitted radiation has higher energy than the incident photon energy. So for the case of anti-Stokes line, the S branch line to the high wave number side of the exciting line. So this left schematic represents the possible allowed transitions involved in the Stokes and anti-Stokes line. Here we can see the transitions are allowed by the selection rule till G equals to 2. So for the Stokes line, we'll have the transitions either from J equals to 0 to 2 or 1 to 3 or 2 to 4 and so on. And for the anti-Stokes line, we will have the transitions either from 5 to 3 or 4 to 2 and so on. And if we consider the spectrum from this transition, then we'll have the central line which has the same energy as the incident photon, that is nu Ex bar. The first transition that corresponds to the 0 for j equals to 0 will have the separation 6b from the central line on the both sides. So left side's spectral lines will give the Stokes line and the right hand side spectral lines will give the anti-Stokes line. But the transition starts from the j equals to 1 or j equals to 2 for the anti-Stokes line will have the separation 4b. Similar case happens for the Stokes line also. In the left side, you can see for j equals to 1 or j equals to 2, we'll have the separation between the spectral line is 4b. So that is the energy difference between two consecutive spectral line. Now, coming to the solution part of the given question. So we have already seen the wave number difference between two consecutive S branch lines of the rotational Raman spectra is 4b. Now it is given in the question that for the diatomic atom H2 gas, that is the hydrogen gas, 4b equals to 243.2 centimeter inverse. So from this we can calculate the rotational constant for the hydrogen gas system. So for that B equals to 60.8 centimeter inverse. Now it is given that the wavelength of the exciting line, that is lambda Ex, equals to 514.5 nanometer. So we'll convert this in terms of wave number. So the wave number of the exciting line, that is nu Ex bar, equals to 1 by lambda Ex. So that is 1 by 514.5 nanometer. So this will give the wave number of the exciting line nu Ex bar equals to 19,436.4 centimeter inverse. Now it is given in the question that the Stokes line appeared at the wave number nu S bar equals to 17,611.4 centimeter inverse. So therefore we can write nu Ex bar minus nu S bar, that is equal to 19,436.4 centimeter inverse, that is for nu Ex bar that we have calculated in the previous slide, minus 17,611.4, that is coming that is given in the question. So this will give 1,825 centimeter inverse. So if we want to represent this quantity in terms of B, that is the rotational constant of the system, then what we will do, we will divide this quantity by 60.8 and multiply 60.8. So this 60.8 is B for our system. So and this quantity 1825 by 60.8 will give roughly 30. So this quantity is roughly 30 B centimeter inverse. So this gives the shift of Stokes line from the central line or the exciting line nu Ex bar. Now to find the rotational energy levels between those the transition happens with Stokes shift that we have calculated in the previous slide, that is 30 B centimeter inverse. Now from the working formula we have seen nu Ex bar minus nu S bar for the Stokes line equals to B times 4j plus 6. So we will equate this B times 4j plus 6 with 30B. So this will give j equals to 6. So that is the rotational quantum number of the lower state from which the transition is happening. So the transition from energy level 6 to 8 will give the S branch Stokes line with wave number 17,611.4 centimeter inverse, that is given in the question. So the next possible Stokes line, the transition will occur at j equals to 7 to j equals to 9. Now we'll calculate the same thing for the transitions from j equals to 7 to j equals to 9. So for that transition, nu Ex bar minus nu S bar equals to B times 4j plus 6 centimeter inverse. So for this transition, j will be 7 here. So we'll put j equals to 7 here. We'll get nu Ex bar minus nu S bar equals to B times 4 into 7 plus 6 centimeter inverse. So that will give 34 times B centimeter inverse. Now B for this hydrogen gas system, we have calculated already, that is 60.8 centimeter inverse. So we'll put here, so we'll get nu Ex bar minus nu S bar equals to 34 times 60.8 centimeter inverse, which will give 2067.2 centimeter inverse. So for the transition from j equals to 7 to 9, the wave number of the Stokes line nu S bar equals to nu Ex bar minus this quantity, that is 2067.2 centimeter inverse. We have already calculated the wave number for the exciting radiation, that is 19,436.4. So we'll put it here and we'll get nu S bar equals to 19,436.4 minus 2067.2 centimeter inverse. So this will give the S branch Stokes line, the wave number of the S branch Stokes line equals to 17,369.2 centimeter inverse. So if we just round it off to the integer form, then we will have the nu S bar for this transition equals to 17,369 centimeter inverse. So this is our desired answer for this question. So we solved this problem and we found that the wave number rounded off to the nearest integer in centimeter inverse at which the Stokes line will appear for the next higher energy level is at 17,369 centimeter inverse.